to question one, please. Question number one. We'll teach you a couple of more minutes to do question 1 again. Then I'll show you how to do it. Okay, guys, so let's see how we can do question 1. I know some of you have done it. So let's see how we can do question 1, part 1. You have these two estimators and we want to see if they are unbiased or not, right? Well, we want to see if they are unbiased. Remember, an estimator is unbiased if the bias is 0, right? So what you need to work out is the bias of the two estimators. The bias, as I told you, is defined as the expected value minus the parameter that you're trying to estimate, right? So this will be the expected value of and if you take the if you take the expectation inside, you get a third of the expectation of x1 plus the expectation of x2 plus the expectation of x3. Yeah. Now we are told the question says that x1 to x3 all have the normal with mean, mu, and variance sigma squared. So what this means is that this guy here is mu, this guy here is also mu, and this one also mu. Right? So this is 0. So this implies that the first estimator is unbiased because the bias is 0. And the same thing for the second estimator. So let's look at the second estimator, which is right? Now, once again, you should take the expectation inside. You get a quarter times, in brackets, the expectation of x1 plus 2 times the expectation of x2 plus the expectation of x3. Alright guys, now we know that each of the expectation is equal to mu, so this is mu plus 2 mu plus mu, right, in brackets, take away mu, and once again this is clearly equal to 0, right? So the conclusion is that both estimators are unbiased estimators for mu, right? I'm sure all of you did this right, yeah? Okay, good. Now the second part is to find the variance of the two estimators. So let's start with the first estimator. So this is question 1, part 2. The variance of mu1 hat is going to be the variance of Now I'm going to take the 3 outside of the brackets. So remember, when you take a constant outside, you need to square it. So 3 becomes 9. And in brackets you have variance of x1, variance of x2 plus the variance of x3. Now we know that each x has a normal. That's what the question says. The question says each is normal with variance sigma squared. So this guy here will be equal to sigma squared. This 2 is sigma squared. This 2 is sigma squared. All right? And if you simplify this will be sigma squared by 3. Okay? Now, the same thing for the variance of, so this is going to be the variance of right? Now you should take the constant outside, making sure to square them. You will get 1 over 16 in brackets variance of x1 plus 4 times the variance of x2 plus variance of x3. Yeah? Now we know each of these guys is sigma squared, so this is going to be sigma squared plus 4 sigma squared plus sigma squared. Alright, so if you simplify this will be 3 sigma squared divided by 8. Alright, so that completes part 2. Part 3, so we haven't completed. Which estimator is the better one? Remember, the estimator that is better is the one that has a smaller variance. So which one is smaller?
I think first. So first one. So
yeah. So since sigma squared by 3 is less than 3 sigma squared by 8, we prefer mu1 hat to mu2 hat. So the first estimator is a better estimator because it has smaller variance, right? Alright guys? Alright, now the last part is asking you to find the sampling distribution of the two estimators. Remember, one of the properties I mentioned to you I don't know whether maybe you forgot. One of the properties I mentioned a long time ago is that if you have a linear combination of independent normal, then that itself is a normal random variable. Do you remember that or not? Well, it was one of the properties I stated when I talked about the normal distribution, right? So using that property, you can answer this question. Question 1, part 3. The first estimator, which is mu1 hat, is going to be normal with the mean. We have already worked out the mean to be mu, and the variance we have worked out is to be sigma squared by 3. Remember, the mean was mu because the bias was 0, which means the mean must have been equal to mu. And sigma squared by 3 is what we got exactly when in the previous step here, sigma squared by 3, right? And similarly, for the second estimator, it too has a normal distribution with the mean equal to mu and the variance equal to 3 sigma squared by 8. Okay? All right. So that completes question 1. Can you do the next question, please? Question 2. Are you guys okay with it, by the way? Any questions on question 1? So go to question 2, please. Just a hint. Okay, can you have a look, please? For question 2, it will be useful to use the following property. Remember, in week 2, when we talked about the normal distribution. Right? One of the properties I mentioned is the following. I don't know whether you recall this or not, but one of the properties I mentioned is property number 6. So that is, if you have a random sample from a normal, then the sample mean is also normal with these parameters. So try to use this property to do question 2, property number 6. That is, if you have a random sample from a normal with parameters mu and sigma squared, then the sample mean itself is also normal with parameters mu and sigma squared by n. Okay, it will be easier if you use this property to do question 2. Okay. Okay. Guys, did you done question 2 yet? Okay, let's see it. So try to use this property number 6, right? Okay, let's go back to where I was. All right, so this is, so you have two random samples, size n1 and n2, and these are the sample means, x bar 1, x bar 2, right? So using the property that I just mentioned, right, x bar 1 will be normal with parameters mu and this one, right? And x bar 2 will be normal with these parameters. So this is by property number 6, which I just mentioned to you, right? So you need to use this property. You can do it also without using these properties, but it will be longer. It'll be easier if you do it using these properties, right? So you have this estimator. All right. The first thing we want to show is that this is unbiased for mu, right? So what you need to find is to show that the bias of this estimator is 0, right? So this is going to be the expectation like this. Okay, guys? Okay. Let me know. So if you're not following what I'm doing, just give a shout, okay? I'm happy to explain better. Right? Now we know from these two statements here that the expectation of x bar 1 must be mu, and the expectation of x bar 2 must also be mu. So this is a mu plus 1 minus a mu minus mu, which is clearly 0, right? So we have shown that mu hat is unbiased. It's an unbiased estimator for mu. The second part is to find the variance. So to find the variance of mu hat, we're going to take the variance of this, right? Now these two are independent variables because we have two independent random samples, right? So you can take the variance inside. A will become a squared times the variance of x bar 1, and 1 minus a will become 1 minus a squared times the variance of x bar 2. Now we know from these two statements, what the variances are. So this is going to be a squared times sigma squared divided by n1 plus 1 minus a squared times sigma squared divided by n2. Okay? You guys with me so far? Yeah? Now sigma squared is something common. So you can write this as follows. You can write this as a squared divided by n1 plus 1 minus a squared divided by n2 in brackets and sigma squared outside. Now you are asked to minimize this function with respect to a. Now this goes back to your calculus. Do you know how, like in calculus, you must have learned how to minimize a function? What do you do?
Differentiate it.
Differentiate it, yeah. So you need to differentiate this function with, we want to minimize it with respect to a, right? So let's differentiate the variance of mu hat with respect to a, right? I'm sure all of you know differentiation better than I do. So you get 2a divided by n1 minus 2 times 1 minus a divided by n2 times sigma squared, and you set this to 0. Now I'm sure you know how to solve this, but I'm not going to spend my time solving it. But if you do solve this, you will get the solution. You will get this as the solution for A. Now, to make sure that this is a minimum, to make sure that this solution corresponds to a minimum, you need to find the second order derivative and show that is positive, right? Okay, so let's do that now. So let's find the second order derivative with respect to A. So here we are. So d2 of the variance of mu hat dA. Alright, differentiate it. Again, you get 2 divided by n1 plus 2 divided by n2 in brackets multiplied by sigma squared, which is clearly positive. Right? So since the second order derivative is positive, this solution here must correspond to minimum. So what this implies is that right? All of you okay with this or not? You should not give a shout. I'm happy to go over. Are you guys okay? Sure? Alright, can you do the next one, please? Question 3. If not okay, just leave me. Must be the way it must be. Please. Okay. Guys, can you do question 3, please? So this is question number 3 here. Guys, are you okay? All right, let's begin with question number 3. So you have this is clearly a continuous distribution, so you need to do some kind of integration, right? So let's look at question 3, part 1. We want to find the bias. We want to find the bias of x bar, the sample mean, right? Which, as you know, is defined as the expectation minus delta. Delta is the parameter that we're trying to estimate, right? So this is expectation of the sample mean, which is take the expectation inside, you get 1 over n times sum of the expectation of xi minus delta. Now, to find the expectation of xi, you need to do some kind of integration because you are given the density, right? So I'm sure you know from probability 1 or even before that, to find the expectation of this, you need to integrate x times the density function, which is this, dx, and the limits of integration are from delta to infinity. All right? Now, any ideas how you can do the integration?
By parts.
Yeah. I know you guys, you probably learned parts in your nursery or something. Yeah. So what you have here is integration. Well, there are many ways you can do this integration. One way is to use parts, right? So let's do integration by parts, right? So if you do integration by parts, this will become all right. So you need to select this term. Well, the wise thing to do is to select this term for differentiation and this for integration. So use this for integration, use this for differentiation, right? So you get this, right? And then minus minus. I know it kind of looks complicated. Are you guys with me or not? I just applied integration by parts. And you must have learned it a long time ago, guys. Integration by parts, right? So you should take this is delta. The limit at infinity is 0. The limit at delta is gonna be this. Then the minus minus is plus. The integral of this guy is not hard. It's this guy here. Then you take the limits from delta to infinity. Put this in brackets. Minus delta. All right. I hope you are not lost. I hope you can still follow me. So this will be E of delta divided by n sum minus minus is delta, and the limit at infinity is 0 once again, and the limit at delta is minus this, right? Like this, all right? Minus minus is plus, so it becomes delta plus 1, and this will, so what you have is the sum of delta plus 1 minus delta. And now the sum of a constant is, remember, is n times the constant. So what you have is 1 over n times delta plus 1 minus delta, which is equal to 1. So the bias of the estimator is equal to 1, which is not a good thing, because what this implies is that x bar is a biased estimator, because the bias is not equal to 0. Remember, if the bias is 0, then the estimator is unbiased, but in this case it's not unbiased. Right, so that's the first part. The second part is to derive an expression for bias, which we have already done. The third part is to, can you propose an alternative unbiased estimator for delta? Yeah, can you? I'm asking you guys. Can you propose the alternative? So we have already done part 1. We have already done part 2, because part 2 is basically the expression for bias, which we already got here, which is delta plus 1. Right? Part 3 is asking you, like, can you propose an alternative unbiased estimator for delta? And what would that be, you think? I'm asking you guys. Can you propose an alternative estimator? It's not difficult to see what it should be.
Oh, that's about. So we want the bias to be 0, so delta plus 1 equals 0, and delta equals minus 1.
Delta, sorry?
Delta equals minus 1, because like you want delta plus 1 to equal 0.
Yeah, but delta is a parameter, so and the estimator must be a function of the data only. It should not involve the parameter that you're trying to estimate. Come on, guys, it's not difficult. Can you see? All right, set y equal to x bar plus 1 as an alternative estimator of delta. Then the bias of y is the expectation of y minus delta, which is the expectation of x bar plus 1 minus delta, which is the expectation of x bar plus 1. Sorry, what did I do? Sorry, it should have been minus 1. Sorry, I'm being stupid here. It should have been minus. Sorry, excuse me for this. Right? So I should have defined the estimator to be x bar minus 1, not plus 1. I apologize. Okay? Now, expectation of x bar, we know. The expectation of x bar, we know from the previous part, is delta plus 1. Right? So this is 0. Alright? So what this implies is that y defined as x bar minus 1 is an unbiased estimator of delta. Do you follow what my argument or not? Yes or no? You okay?
Why is the bias x delta plus 1?
That's because of what we showed in previous part here. Remember, the bias of x bar is the expectation minus this, right? And we showed here that the expectation of x bar is delta plus 1, because these two guys cancel out. Huh? You don't follow? Because remember, This is the expectation minus delta, right? So, and be sure that the expectation of x bar, which is this guy here, is equal to delta plus 1.
So wouldn't the bias just be 1?
Yeah, the bias is 1, yeah, for the first part, yeah. For the first part, the bias will be 1, yes.
So why is it delta plus 1 in the second part?
Sorry, can you come again?
In the second part of the question, why is the bias delta plus 1?
Oh, yeah, sorry, yeah, it should have been 1, sorry, excuse me. That's another stupid miss. It should have been 1, yeah. Sorry, my apologies once again. Yeah, the answer should have been 1, yeah. Thank you for pointing that out, thank you. Yeah. So, yeah, I mean, in part 3, you see what I've done in part 3 is to create a new estimator that has bias equal to 0, and hence that estimator should be unbiased. Yeah. Okay, guys. Any other questions, guys? Hello, guys. Any other questions on question number 3? All right. You can see the full solutions and the video solution and the handwritten solution and the typed solution all on the course website. All right. So I'll see you guys later this week. And as usual, if you have any questions, just feel free to contact me 24/7. Okay. Hi.
Wondering, when or is there going to be a midterm test?
There's no midterm. It's just the coursework, which is our coursework, which is due on the 20th of May, I think.
Oh, okay.
It's on the 20th of May. Yeah. If you look at the course website, you will see that. Let me check. Yeah, it's on the 20th of May. The coursework is due, but there's no in-class test for this course.
Okay.
Yeah. Yeah.
Thank you.
Bye. 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 Bye.